Question 6. If we are to consider the complex number w, which equals z plus I over z plus 2, where z equals x plus iy, and I is the usual square root of negative 1. Then, if w equals I, determine z in the form z equals r cis theta. The first thing we would have to do is to write that down. So, I equals z plus I over z plus 2. And then we're going to rearrange to make z the subject. So, multiply by z plus 2, we get I times z plus 2 equals z plus I. Then, expanding the brackets, iz plus 2i equals z plus I. Now let's rearrange to get all of the values of z on one side. iz minus z equals minus I, because we've subtracted 2i from both sides. And so z, putting into brackets, z minus 1 plus I equals minus I. So, z equals minus I divided by minus 1 plus I. We can divide top and bottom by minus 1 to get that's equal to I over 1 minus I. But we need it in the form r cis theta, so we need to make the denominator real, multiply by its conjugate there. So we can say that is I 1 plus I over 1 minus I 1 plus I, which is minus 1 plus I over 2. Which means we have in Cartesian form minus a half plus a half I. In order to put it into r cis theta form, we then need to find the modulus of z and then the argument of z. So, modulus of z would be minus a half squared plus a half squared, all square rooted, which would give us the square root of a quarter plus a quarter, which is the square root of a half, which is 1 over root 2. Or, if you like, root 2 over 2. The argument of z would be, if we draw an argan diagram here, then the argument of z would give us, we can see clearly that z, the argument of z, must be some multiple of pi by 4. It's tan to the minus 1, a half over minus a half, which is tan to the minus 1 of minus 1, which, looking at our argand diagram, gives us 3 pi by 4. So, putting it into the form that is required, z equals 1 over root 2 cis 3 pi by 4. Okay, part B asks us to prove that w equals to this nasty formula. So the first thing that we're going to do is take our value of w, z plus I over z plus 2, and multiply it by, well, substitute in x. Z is x plus iy, plus I on the top, plus 2 on the bottom. And let's separate it into its real and imaginary parts, both the top and the bottom. X plus I, y plus 1, over x plus 2, plus iy. Now we're going to want to multiply the bottom by its complex conjugate. So, we have x plus iy at the top there, multiplied by the complex conjugate, x plus 2 minus iy, and the bottom multiplied by its complex conjugate. There you go. That's going to be equal to, the bottom is simple, it's x plus 2 squared plus y squared, because that would be minus I squared y squared, which is plus y squared. And the top, a little bit more complicated, but we just expand it as if it's a quadratic equation. It'll take a little bit, x times x plus 2, take away ixy plus I y plus 1 times x plus 2. Let's move all this around just so it creates a bit more space. And then we're going to subtract I squared y plus 1. Okay, now let's simplify that. Simplify the top, the bottom's going to remain the same. So we have x squared plus 2x minus iy squared plus ixy minus i2y plus ix plus 2i plus y squared plus y. Don't need that. So therefore we can say that w is equal to, now let us separate this into real and imaginary parts. The real parts, they're x squared plus 2x plus y squared plus y, which conveniently is what we need if you look at the question. And the imaginary parts, we can do a bit of simplifying. We've got minus ixy and plus ixy, we can cancel those. So we're left with I times x plus 2y plus 2 all over the bottom there. We have x plus 2 all squared plus y squared as required. Part C, we said hence, which means we must use that formula that we've got. Show that when real w equals 1, the points xy line a straight line L1, and write down its gradient. So, if real w equals 1, then the real part, we can ignore the imaginary part for the moment, but the real part, the top of this real part here, divided by the bottom, must equal 1. Okay, good. So, multiplying that out, we get x squared plus 2x plus y squared plus y equals x squared plus 4x plus 4 plus y squared. Conveniently, there's a lot of simplifying that can be done here. Cancel the x squareds, cancel the y squareds, and rearrange, move the 2x to the other side, subtract 2x. We have y equals 2x plus 4, which is clearly a straight line and has a gradient of 2. Which then leaves us just with part D. Given the argument z equals argument w, which equals pi by 4, find the modulus of z. Well, if the argument of z equals 1, then we know that, equals pi by 4, then tan of pi by 4 equals 1. Okay, we can also represent that on an Argand diagram, we'll do that in a minute. So, y over x equals 1, so y equals x. Similarly, if the argument of w equals pi by 4, then by the same reasoning, the imaginary part, it doesn't really matter what the bottom part is here, but the imaginary part of w and the real part of w need to match nicely. So we have here the imaginary part of w, x squared plus 2x plus y squared plus y, needs to equal x plus 2y plus 2. The real part needs to equal the imaginary part, and as we're all dividing by the bottom, it doesn't really matter what the bottom is. So, once again, we can start to simplify here. X equals y, so we can replace every y with an x. We get x squared plus 2x plus x squared plus x equals x plus 2x plus 2. Lots and lots of cancelling. Well, cancel the 2x's anyway and the x's. So we get 2x squared equals 2, which conveniently tells us that x squared equals 1. Looking at our Argand diagram here, if we have our real and imaginary parts, we can see that clearly both x and y must be positive. So x squared equals plus or minus 1, but can't be greater than 0, so x equals 1, which means y also equals 1. So finally, the modulus of z equals the square root of 1 squared plus 1 squared, which equals the square root of 2.